today we are going to be talking about a few more ways that you can feed input and get output of your program, as well as how you can chunk your program down into little bits that as well will have these input and output kinds of mechanisms. So the first that we're going to talk about in this case is redirection and pipes. These are tools built into your operating system's shell that allow you to feed in input from the operating system into the program without necessarily having to use a file or having to use the network. Instead, by typing certain things into the shell, you can feed in large or small amounts of input into your program and take the output from the program and direct it into various places. This is an example of the input redirection operator. This operator takes a file descriptor, or the name of a file as we'll call it for the moment, and allows you to take whatever is inside the file and feed it in not as an argument to the program, but as the actual input to the program, such as the same as you would type. So remember, in many of the sample programs that we've been going through, you type in input until you press Control-D, and when you press Control-D, the operating system sends a signal to your program that there's no more input to receive. This is the end of file marker. However, you can simulate this with pre-prepared text that's in a file already using the input redirection operator. So in this case, my prog would receive the entire contents of words.txt, and when words.txt is done, it would get an end of file descriptor, so you wouldn't be able to type anything in anymore. Just like we have an input operator, we also have one for output. One thing to note about the output redirection operator is that it actually redirects anything that you would have seen on screen to the file, and so you won't necessarily see any output on screen anymore. Let's try this out with a series of programs that we'll test out for the input and output redirection operators. Open readloop1.c. This program is going to allow us to read in a series of numbers, one after the other. When we're done reading in the series of numbers, you can either press Control-D to let the computer know that we're done reading things in, or alternately, if we're using an input redirection operator, when the program has consumed the entirety of the file, it will end. And after that, what are we going to do? Let's take a look at our program. The first thing we do is set a variable max to whatever was just input. The first number that was input, as we see here by the %d format specifier. After we've read in at least one number, where we'll set n equals 1, so that'll be the number of numbers that we've read in. The maximum number that we've read in when we're just starting off is obviously the very first one, and then we enter a while loop. Look at the condition particularly in this while loop. The condition is checking the output of scanf. Is the output of scanf 1? We read in exactly one thing from the command line. If we have read in one thing, do what's in the loop body. If we haven't read in one thing, that means there is no more input coming in, and it's time to print out the results of our computation. So now let's look at the body of the loop. In the body of the loop, we check if the number that we read in inside the loop just now is bigger than max. If it is bigger than max, we know we've found our new maximum, and so set max equal to the thing we just read in. We also increment the counter n that tells us how many things we've read in, and then we go back to the start of the loop again. Remember, the way the loops work is we start off by checking the condition. If the condition passes, we move directly to the body of the loop. So let's give this a run. And wait for it to compile. There we go. So let's type in a few numbers. Okay. 7 values read, maximum is 475, the program gets it right. Now let's just make sure that it wasn't reading in the very last one and only reporting that one. Let's try it again. It correctly is able to ascertain what the largest value is that we entered in. Now let's try it with a file. So let's create a new file in this directory. I'll go up here and sumnums is what I'll call this file. And in sumnums, I will just put some different numbers in. I'm not even paying much attention to what I'm typing in. Now I'm going to use the input redirection operator, and I'm going to give it the name of the file I just created, sumnums. And let's see what we get. I had 9 things in that file, and the maximum one was 4,673,627. Great. What happens if I do output redirection? What do we get? So let's try this. Sumnums output. It's not a very friendly file name, but you'll see now at the bottom here, there was nothing that was printed to the screen. All the output from the program has been redirected and into a file called sumnums output. So now if I click on sumnums output, I see all the outputs from the text that we would have otherwise seen in the terminal. We have one other example that we'll take a brief look at. And this one is called fortcom.c for those of you following along. This program is starting to get a little more complicated, but is still only using the basic building blocks that we have observed so far. So I'll scroll down a little more so that you can see a bit more of the program. Here we have a new function that we haven't yet encountered in this class, and this is getChar. getChar is quite similar to scanf, except it's actually a simpler and more fundamental function that is built into the POSIX standard. For those of you who've been paying attention to ed, POSIX is a standard for operating systems that specifies a way of getting data in and out of a certain class of systems that adhere to it. This includes Linux and to a certain extent Mac OS. Now Mac OS doesn't exactly observe POSIX, so you might find that things aren't exactly what it says in the Linux or Unix man pages, but for much of the time we can get away with it. Back to our function getChar, it does exactly what you'd expect. It asks the user for a single character of input and returns the value. You'll notice that unlike scanf, we don't give it the name of a variable as an argument to the function. Instead, the return value from the function is the way that we are able to access the character that has been requested from the user. You can see this clearly in the syntax. ch, which is a character that we've declared, is being set to the output from getChar. Now you might notice something funny I just said. I said that ch is a character, but over here I've declared it as an integer. Why might that still be an okay thing to do? Thinking back to one of our past lectures, how come we can put a character into an integer? Yeah, and
because characters are made of ASCII and they have numbers.
Exactly. Characters are just numbers. Internally inside the computer, they're represented by their corresponding ASCII numeral. And so, given that an integer type is larger than a character type, we know that we can fit the entire character into an integer that we declare. We are asking the computer to reserve a bit of extra memory that we don't need. However, it will still work. The other thing to note here is the fact that we are taking the output from this assignment and then comparing it to EOF. Now, EOF, as I mentioned a few moments ago, is a special marker that stands for end of file. EOF, end of file. When the computer has finished reading in input, when you press Command D in your terminal, a special signal gets sent to the program that means the next character that's read will be set to this special value EOF. Now, EOF is just an ASCII encoded number, but instead of representing one of the normal numbers or symbols, it is a special marker value. A marker value that the operating system uses to tell the program running that it should stop reading any more input. If you do try to read more input after EOF, you'll get one of a variety of a different sort of errors depending on exactly which function you're using to try and read past the end of the file. So what happens in this statement here is ch gets set to the value of getChar. The result of evaluating this set of parens is going to be that same value, and then we can compare it to EOF. Remember, the value of an assignment is the thing that was actually being set to. If I set x equal to 5, the result of x equals 5 is 5. If I set ch to 5, the result of this paren over here will itself be 5. Then we're checking if 5 does not equal EOF, and let's do something more realistic. Capital A is 65. So if getChar is read in a capital A, ch is 65, and 65 is not equal to EOF, and so we go inside here. You can see that there is a lot of sophistication packed into one very small line of C. We're using a number of our different concepts, and we're only two lines into our program. So now that we're past the guard for our loop, let's see what we're actually doing. If ch equals c and new line last is equal to 1 or is non-zero, mark that we're in a comment. What this is doing is it's checking to see if we are in a Fortran style comment, and a Fortran style comment is a line that instead of beginning with one of these funny slash patterns like we have in C, begins with the letter C. So check if the current character that we just read in is the letter C, and check to see that we're at the start of a new line. When this program is initially run and hasn't read in any input, we know we're at the start of the line because we haven't read in anything yet. But after that first character, we're going to need to change that value. This is what we call a flag. It is letting us know if something is true or false, and we set and update it based on the progress of our program. Let's see how the guard changes. If we're not in a comment, putChar, here's another function. PutChar is just like print, but for a single character and takes a single argument. So if we're not in a comment, print the value of the character we just read to screen. If the character is a new line, then reset whether we're in a comment or not, but also set the flag that says we're at the start of a new line. Otherwise, if it's anything other than a new line, tell the flag that we are not at the start of the line anymore, and therefore if there's a capital letter C that appears somewhere else in that line, that doesn't mean it's a comment. This is making sure that we're only going into this special don't show the comment routine as long as there is a C at the capital C at the very start of the line. So to go through the logic one more time, if we see a capital C and the flag for a new line is set, mark that we're in a comment. If we're not in a comment, print the letter to screen. If you get to a new line, reset whether in a comment or not, and set the fact that we just saw a new line. And otherwise, if we've seen anything else, make sure that the computer knows that we haven't just seen a new line. We're still in the middle of a sentence. And then return 0. Let's give this a run. I'm not sure if I have a pre-built Fortran program for us to use this with, but we can make a fake one. We'll call this pretend Fortran. Okay, so there is our fake Fortran program. Now, despite the fact that this is not actually Fortran, all the lines that start with a capital C are still in the form of a Fortran comment. Then, when I run this program, I should see, I wish I were a Fortran program, sad face, without the two comments. Let's give it a run and see what happens. So does someone want to yell out what I'm going to type in to run my program? The the source code was called fortcom.c. So how do I compile and run fortcom.c? Clang, slow it down a little bit. Clang, fortcom.c. -o. Fortcom. Now to run it with this pretend Fortran program, what am I going to write? Nope. .text is more for the user than for the operating system. For the operating system, all files are the same, except for the fact that your operating system will sometimes look at whatever comes after the last dot to figure out what program it should open it with, just as a convenience to the user. It's not actually necessary to the file type itself. So you can see there, I wish I were a Fortran program, sad face, our program works. We've learned about the input redirection operator and the output redirection operator, but we still have one of the most powerful shell operators available to us. And this is the beautiful pipe. Now, it may not look like a pipe, but if we go back to our, beautiful picture here, we can see Mario in the pipe. Whenever you see one of those bar lines, just think of that Mario pipe. And this is located on your keyboard. I'm going to lift up the keyboard and show you. This is located on your keyboard above the return button on that backslash. So to write a pipe, you hold down Shift, you press that button, and you get the pipe symbol. And that is also used for doing the double pipe symbol, which is the OR operator in C. Okay, now let me return my keyboard before someone from field services comes and accuses me of breaking that as well as the HDMI. So what does the pipe operator do? Let's say that we want to build a chain of programs. Program 1 gets fed in some input, and the output of program 1 we want to go to program 2, and the output of program 2 we want to go to program 3. One way of doing this would be to create a whole bunch of files. So we would have one file that's called program 1 output, and then we feed program 1 output into program 2, and then we create a new file, program 2 output, and feed that file into program 3. That would work, but it's a little inefficient, and in particular, it's not quite in keeping with the Unix philosophy, which is that every program should do one thing, do it well, and then be able to chain that directly into another program. And this is what the piping operator is for. This allows us to do the chaining. So let's see how this works. Here I've got 3 Unix or Linux commands, cat, grep, and t. These may be new to some of you, so I'll tell you what each of them does. Cat prints out to the screen the contents of a file. So cat will print out words.txt. Grep is a program that finds text within the input. In this case, the simplest input we can give it is both some text in which to search and a substring that we're searching for. We're going to search for the substring D. And then T is another useful utility that will print out not the contents of its input, not only to the screen, but also to a file at the same time. But I'm not going to use T. I'm actually going to use a different program at the end, and this will be a fun one, I think, or at least slightly amusing to some of you. Ooh. I probably have to do my... So let's look for a nice long program. Okay, this one is long enough, sphere.c. We haven't looked at it yet, but it'll serve our purposes. So remember what we were going to do is run cat, and this was sphere.c. Let's see what the output of that is. It prints the contents of sphere.c to the screen. Now let's pipe that. We're going to pipe the output of sphere.c into grep, and we're going to put in D. So this will give us all the lines in sphere.c that contain the letter D somewhere in the line. And now instead of T, which would just print the same thing out again, I'm going to use another program called tac. Anyone ever guess what tac does? I've told you what cat does. What might tac do? Backwards, exactly. Tac is cat backwards. Let's see it in action. In our previous output, we had this double volume line last. Now our double volume line is first. Using a combination of these utilities, you can do some fairly sophisticated string manipulation. Of course, Unix is not just limited to these 3 or 4 different commands that I've told you about. There are a large variety of very simple utilities that you can combine together in order to do quite sophisticated and useful work. In fact, now this is a little bonus. So these programs, each on their own, may seem trivial and not super useful, but combined, they're quite powerful. I should have remembered, not working today. Switching tacks. I want to talk about prime numbers for a couple minutes. And this might seem totally out of the blue, but with just the tools that we've got so far, we can actually do quite a lot. And one of the things that we can do is find and use prime numbers. Now, this might not seem interesting at first, but it turns out that prime numbers are important not only to mathematics, but to a lot of cryptography. Before we get there though, we're going to need to find some prime numbers, and this is a harder task than it might sound. There's no obvious pattern to the layout of prime numbers in the set of all numbers. In fact, if you solve this problem again, if you can figure out a way to easily come up with the full list of prime numbers, you'll probably get 100 in the course, and we can arrange $1 million in prize money for you as well. So we can add this to our 3 ends challenge for the set of problems with which you could get 100 in Foundations of Algorithms. Again, probably don't encourage you to spend your time working on this one. You're better off doing the grok exercises. But if you do solve it, come find me and you'll get more than just a chocolate. What would one strategy be for finding these prime numbers? Well, we could find a maybe prime number, and then we could check if it's still maybe a prime, run some little tests on it. Is it divisible by 2? Is it divisible by 3? Is it divisible by 5? Is it divisible by other prime numbers? And if we find that all the prime numbers smaller, that it doesn't divide by any of the prime numbers smaller than it, then we know that it's going to be a prime as well. We have a program that can do this. And let's check it out. We start off with asking the user for input for the maybe prime. Later we'll find a way to get all the prime numbers up to a certain number, but for the time being we just want to check if a given number is prime. Let's say the question is 27 prime? So the first thing we do is we ask the user for input, what number do you want to test? And then we set is prime equals 1. This is going to tell us at the end of the program whether the number that we've read in is prime or not. Now right now this is just a flag. We're setting the flag to 1, and if we find something that contradicts our assumption that it is prime, then we set it to 0. You can think of this just like in mathematics, how sometimes you do a proof by contradiction, where you start off assuming the thing that you want to prove, even though it might be false. So we start with it here. We're assuming that the number is prime, and then we're going to go and check for a counterfactual that would prove, a counter-argument that would prove that it is not the case. And a contradiction in this case is finding any number that it divides by, because of course a prime number shouldn't have any divisors other than 1 and itself. So if we can find something between 2 and inclusive and the number itself, we know that the number is not prime. Now, another thing you'll note here is I'm not actually going all the way up to the number itself. I'm only going up to the square root of the number. Why might this be? This is a mathematics question rather than a computer science question, although the two are deeply linked. Yeah. Remind me name again? Leto. Yeah, Leto's right. Factors come in pairs, and so if you have found one of the factors that's the small factor multiplied by the bigger factor, then you would have already found it when checking the smaller factor. If you're getting bigger than the square root, that means that you're already going to have found the larger factor's pair, its small pair, and so when we perform our check, we would have already revealed this larger factor. So you only need to go up to the square root. Let's again go to the overall structure of our loop. Let's start searching for potential divisors at 2, stop when we get to the square root, and each next number is a potential divisor. Then we have our check for our contradiction. if n divides by the divisor, so if there is no remainder at the end of the division, then we know that it is not a prime. We'll find something else that it divides by. So set our contradiction flag. It isn't prime, we now know, and exit from the loop. If this loop terminates, but we never get to this bit in the middle, if we have never found a divisor, then we know that the number must be prime. There are no divisors in the entire space in which there could have been one. Then we just print our result. So let's give this a run. Clang. And now I'm going to use my nice flags variable that has all the dash wall, dash sanitizer, dash all of those things, because I got it working for this class. And let's create the program is prime. And just so you can see, there's my nice long set of flags that will help me detect errors, and I'll put this up on ed for any of you to use if you want. Okay, let's run is prime. It's asking me for a number. Remember, enter a number n over here. Let's enter the number 4. 4 equals 2 by 2. It's found a divisor, and so it is not prime. Let's try it with a prime number. Let's try it, with a... and you can see that once we put in a prime number, it is not able to find any factors in the range, and so it prints out is a prime number. Now, if we try a big number, it's still pretty fast. Oh. Did I accidentally put in something divisible by 2? Yes, I did. Well, that would have been easy to solve. Trial division is used for figuring out what numbers make up a larger number. This is called integer factorization. If we want to find the sequence of primes that we can use to make a larger number, this is integer factorization. Any larger number can be made up by a product of smaller numbers unless it is a prime. And this turns out to be very important in code breaking. The fact that prime numbers are actually useful and that all this number theory is somehow going to be used for something in the real world was quite surprising to the guy who came up with quite a lot of this. His name was G.H. Hardy, and he was a 19th century mathematician. And at that time, it was not known that prime numbers were going to be useful for anything, or that any of this algebraic number theory was going to be useful for anything. And so he was so proud of the fact that his work was totally abstract, that the mathematics that he was doing had no impact on the real world whatsoever. He said, "I've never done anything useful. No discovery of mine has made, or is likely to make directly or indirectly, for good or for ill, the least difference to the amenity of the world." Now, I want to stay on this point for a second because it's quite important to your role as potential programmers and computer scientists in the world. While you might think naively that the programs that you're writing are just a matter of engineering, they don't have impact on the world around you and are unlikely to have a certain moral weight. As is becoming increasingly clear from both this decade and the past decade, algorithms have quite a powerful impact on society. And so as you go through your career as computer scientists, or at least as people who are able to program competently and design algorithms, I want you to, before actually doing something, and to think if you can do it, to think if you should do it. Many algorithms are used for purposes of mass surveillance, to violate civil liberties, to design systems that have a net negative social impact. And so at this moment in the course, I just wanted to pause for a minute and give you time to process the fact that algorithms, much like all other tools, are not themselves inherently neutral. Algorithms can be designed for a purpose, good or evil, and as you gain these skills, that's something I want you to be consistently aware of, which in the vision of G.H. Hardy was soon proven to be false. So Hardy loved pure mathematics because it wasn't useful. This is the same way that many of you might find that you love computer science because it's so abstract. But computer scientists need to think about ethics. This is what's known as the Diffie-Hellman Key Exchange protocol. And this is, joy of joys, non-accessible. This is just for enrichment. This is what we call a cryptographic communications protocol. It's used to establish a form of secure communications between Alice and Bob, who are trying to protect themselves against Eve, who's standing there at the bottom, Eve the eavesdropper. I use these three names because they are common to almost all descriptions of cryptographic protocols, and the figures are courtesy of XKCD, who routinely uses these figures in its comics. So how does this protocol operate? At the start, both Alice and Bob have never met, but somehow want to generate a piece of secret information that only the two of them know and that no one else can figure out without beating one of them over the head with a lead pipe. So Alice comes up with her own secret number that Bob doesn't know. Bob comes up with a secret number that Alice doesn't know. Let's call Alice's secret number A and Bob's secret number B. And it's particularly important that these numbers be chosen randomly and also that they be pretty big numbers. Exactly how big I'm not going to go into now, but you should know that it forms part of an algebraic group, which hopefully some of you will encounter in second year algebra. So Alice and Bob have their secret numbers, and Alice performs this computation with G, a generator, which is another algebraic term, but we can just assume for the time being that it is the number 2. And there is some prime that they've agreed on and that's public and that everyone can share called P. And the number P should be a really, really big prime. So our isPrime program probably isn't going to be useful for finding these very, very, very large primes. So Alice computes 2 to the A, or G, whatever it happens to be, and then does clockwork arithmetic with the number P. So instead of a clock with 12 places, there are going to be P places. And so raising 2 to the power of A, once we get around to the P place in the clock, we go back to 0 and we start again, and we keep doing this until we've gone around enough to get to the number that is represented by 2 to the A. So this is called modular reduction, doing some mathematical operation, going around till we hit the maximum of our clock, and then keep going around until as many times as we need, till we get to the number we need. Alice computes this number, G to the A mod P, and sends it to Bob. Bob does the same thing with his secret number. He computes G to the B mod P and sends it to Alice. Then, at this point, Alice and Bob can do something special. Look at the bottom corner here for both of them. Alice was just sent G to the B mod P by Bob. If she raises this to the power of A, she gets G to the AB mod P, or G to the BA mod P. These two are the same, G to the AB and G to the BA, by the power of exponentiation. Now let's look what happens when Bob does this. Bob receives G to the A mod P from Alice and raises it to the power of B. And then he gets G to the AB mod P. Now Bob and Alice have the same number on either side, but the only thing that Eve has seen is these large numbers in the middle, G to the A mod P and G to the B mod P. And it is computationally, it is a hypothesis that it is computationally very, very difficult to go from G to the B mod P and figure out what B is, or to go from G to the A mod P and figure out what A is. This is the problem of the discrete logarithm. We're trying to figure out, given G to the A mod P, what A is. Now, if Eve can't figure this out, if she can't come up with one of the values of A and B, she can't combine that value of, let's say, B with G to the A mod P to figure out what Alice and Bob's shared secret is, this secret number that they've got at the end. So assuming that Eve has been unable to come up with these numbers, now Alice and Bob are ready to start encrypting things to each other using this shared secret number. And in this case, we see that Bob, using G to the AB, sends as his secret, which is an important part of encryption, sends the signal to Alice to attack, and Eve mysteriously disappears. There are also a wide variety of other primality testing algorithms. Our trial division one, where we just try all the different combinations, is not the most efficient. And all of these different algorithms have different runtimes. Square root n is not where this story ends. We can go to approximately log n to the 4 or k log squared n, where k is another parameter of the algorithm. And then there's even a simple algorithm that's not these really complicated Miller-Rabin tests that gets us much better than square root n. So here's another example of a very, very important use case of algorithmic improvements in the real world. With this, we've covered all the way up to chapter 4. We've covered iteration, looping, basic C, input and output, and we've even, I think I even mentioned in one of the lectures, do-while loops. Do not use do-while loops. But other than that, pretty much all of the tools that we have covered in the first 2 weeks are at your disposal. And with this, I encourage you to go home over the weekend, try write some fun things, look at the code from the class, explore some new programs, explore some new algorithms, and more than that, have a fantastic weekend, and I will see you next week for functions. Thank you all very much.